Welcome to all of you. Now we discuss the question paper DSCC-2 2024 Group B Basic Algebra Semester 2 CCF. The question paper question 3, answer any two questions. Question 3a, if A is equal to the set 1, 2, 3, 5, then find the equivalence relation corresponding to the partition this set subset 1, subset 2, 3, subset 5 on S. A partition of a set S not equal to phi divides the set into non-empty set, disjoint subset, non-empty disjoint subsets whose union is the entire set. Each of these subsets is an equivalence class. The equivalence relation on S consists of all order pair AB where A and B belong to the same equivalence class. Hence, the given partition is this. Here, this is the set. So, this is the set S, this 1 and this 2, 3 and this 5. This set is S. Now, for this set S, we get a partition. This is the non-empty disjoint subset, and this one, this one, and this one. So we get three subsets. All are disjoint subset. This subset 1, this subset 5, and this subset containing 2 and 3. Now, for these subsets, we get an equivalence class for this set. We equivalence class 1, class 1. Only the possible pair is 1 and 1 order pair. For this equivalence class, either class 2 or class 3, both are same, and so this class contain the set 2, 3. The possible pairs are 2, 2, 2, 3, 3, 2, 3, 3. And for the equivalence class 5 is the set only singleton set containing the element 5. The only possible pair is only the 5, 5. So the equivalence relation is the union of all these sets of pairs. These are equivalence relation. This 1, 1 union, this set 2, 2, 2, 3, 3, 2, 3, 3 union, this order pair 5, 5. Hence, the equivalence relation are corresponding to the partition 1, 2, 3, and 5 on the set S is given by this 1, 1, 2, 2, 2, 3, 3, 2, 3, 3, 5, 5. Question 3b. Show that S less than equal to is a poset where S is the set of all positive divisors of 72 and A less than equal to B means A is a divisor of B for all A comma B belongs to S. Now S with the set of all positive divisors of 72, and so S contains these elements 1, 2, 3, 4, 5, 6, and so 5 6, 8, 9, 12, 18, 24, 36, and itself 72. Relation A less than equal to B is defined as A is a divisor of B. We need to show that this relation is a partial order on the set S by proving it is reflexive, antisymmetric, and transitive. Now, first we prove reflexivity. For a relation to be reflexive, we know that this A less than equal to A for all A belongs to S. This means that A must be a divisor of A. Since any number is a divisor of itself, the 12 is a divisor of 12. So the condition holds. For example, 1 is a divisor of 1, 2 is a divisor of 2, and so on. Thus, a relation is reflexive. Next, second condition to prove antisymmetric. The definition of antisymmetric is this: for any two elements A, B belongs to S, A less than equal to B and B less than equal to A implies A equal to B. This is the relation, this is the condition for antisymmetric relation. Now, A less than equal to B means that A is a divisor of B. That means B equal to some integer K into A, and B less than equal to A means B is a divisor of A, that is A equal to some integer A into B. Substituting the first equation into first substituting the first equation into the second, we get B equal to K into A. So this equals to A, value of A is LB, so put LB. Second, A equal to LB, and value of B is Ka, so put Ka from the first relation. So this is equal to LK into A. Since A is a positive divisor of 72 and A not equal to 0, we can divide by A to get 1 equal to LK. Since K and L are both positive integers, as A, B belongs to S are positive, now we substitute our expressions for C. Let's see condition 1 and 2 into this equation. We use C equal to BK2 in the first term, ACX, and C equal to sorry. So now this is the LK. Solution is K equal to 1 and L equal to 1. This means that A equal to B, thus the relation is antisymmetric. Now we prove the relation is transitive. The relation to be transitive for three elements A, B, C belongs to S, A less than equal to B, and B less than equal to A implies A less than equal to C. Now A less than equal to B means A is a divisor of B, so B equal to Ka for some positive integer K, and B less than equal to C means B is a divisor of C, so C equal to MB for some positive integer M. And substituting the first equation into the second, C equal to MB, here value of B is Ka. Since M and K are positive integers, their product Mk, this Mk, is also positive integer. This means that A is a divisor of C. Thus the relation is transitive. So A is a divisor of C, so A less than equal to C. Hence the relation less than equal to on the set S is of positive divisors of 72 is reflexive, antisymmetric, and transitive. So S less than equal to is a poset. So this implies A less than equal to C. A less than equal to C, A is the divisor of C. Next question, 3C. If A divides C, B divides C, and GCD of AB equal to 1, that is A and B are prime to each other, then so that A into B divides C, where M divides N means M divides N. So M divides N, this means, so 3 divides 6. 3 divides 6. So 6 is divisible by 3. That's mean this. Now, it is given that A divides C, this means C equal to A K1 for some K1 integer belongs to Z. B divides C means C equal to BK2 for some integer K2, and GCD A comma B equal to 1. These three conditions are given. From the property of the greatest common divisor GCD, since GCD A comma B equal to 1, there exist an integer x and y such that ax equal to by, ax plus by equal to 1. This is the property of GCD. We can multiply this both sides by c. By c, this c is this integer. So we get acx plus bcy equal to c. Now we substitute our expressions for c from conditions 1 and 2. Condition 1 is this, c equal to ak1 and c equal to bk2. So we get a bk2 into x plus b bracket ak1 y equal to c. Taking common ab, we get this, and this capital K, k2x plus k1y equal to capital K. Say this capital K belongs to the set of all integers, because k1, k2, x and y are all integers. The definition of divisibility, this equation shows that C is an integer multiple of AB. That means this implies AB divides C. Hence the result. So, question 4a. Find the number of relations which are reflexive as well as symmetric defined on a set containing n elements. Here, S be a set with n elements. So, this contains, say, number of elements of set S is equal to n. The relation on S is a subset of S process. The total number of order pair in S process is n square. A relation R is reflexive if for every elements A belongs to S, the pair A comma A is in R. There are n such diagonal pairs for this matrix, say A, B, C, D, and this A, B, C, D. So for this A comma A, and for the principal diagonal A, B, B, C, C, D, D, and so on. So this order pair A is in R. There are n such diagonal pairs, principal diagonal, along the principal diagonal. For the relation to be reflexive, because here we have to prove this reflection is reflexive and as well as symmetric. So these n pairs, this A, B, B, C, C, up to this, must be included, leaving no choice for them. Relation R is symmetric if whenever A comma B order pair belongs to R with A not equal to B, then BA must also belongs to R. The number of off-diagonal pairs in S process is n square minus n square total number of pairs from the n elements, and minus n these principal diagonal pairs. So off-diagonal pairs is n square minus n. These pairs can be grouped into n square minus n by 2 distinct sets of the form AB and BA. This 1 2 position and 2 1 position, that is IJ position and JI position. For each of these n square minus n by 2 symmetric pairs, we have two choices. Either both pairs are in relation when it is symmetric, and neither is. So choice for one pair is independent of the choice of any other symmetric pair. Therefore, the total number of such relations is given by the number of choices for the off-diagonal pairs, which is two choices for each of these n square minus n by 2 pairs. So for this 2 cross 2 cross 2 into 2, this n square minus n by 2 times, that is 2 to the power n square minus n by 2 number of relation. This relation, number of relations, reflexive as well as symmetric. Note that a set containing n elements, number of reflexive relations is 2 to the power n square minus n. Number of symmetric relations is 2 to the power n square plus n by 2. And number of reflexive and symmetric relations is 2 to the power bracket n square minus 1 n whole divided by 2. And this is the last case for our problem. You can consult this book, Topics in Abstract Algebra, Sen Gosmukopadhyay and Maiti, University Press, 4th edition, 2022, page number 28 to 29. Next question, 4b1, find a bijective mapping from the set N onto the set Z, set of integers. N is the set of all natural numbers, 1, 2, 3, 4, and Z of integers, and 0 plus minus 1, plus minus 2, and so on. Now, from the definition of bijective mapping, a function f maps a to b is bijective or bijection if it satisfies two conditions. That is, it is both injective and surjective also. Now, injective, for the injective mapping, one-to-one mapping, for all a1, a2 belongs to A, is the domain set, if fa1 equal to fa2, then a1 equal to a2. That is, fa1 equal to fa2 implies a1 equal to a2. Alternatively, for all a1, a2 belongs to the domain set A, a1 not equal to a2, pre-image not equal, implies the images are also not equal, fa1 not equal to fa2. Surjective mapping, that is onto mapping, for every element B in the codomain set B, capital B, there exists at least one element A in the domain set A such that fa equal to B. That is, for all B in the codomain set, there exists A, at least one element A belongs to the domain set A such that fa equal to B. Now, we can define bijective mapping F maps from the natural number A into the set of all integers Z can be defined in this way: Fn equal to n by 2 if n is even. So n equal to 2, this 2 by 2, 1. N is equal to 4, this 4 by 2, 2. N equal to 6, this is equal to 6 by 2, 3. And Fn equal to minus bracket n minus 1 whole divided by 2 if n is odd. That is, odd number is, if n equal to 1, then 1 minus 1 by 2, that is 0. And if n equal to 3, then 3 maps to this, 3 maps to 3 minus 1 by 2, that is equal to minus 1. This 0, minus 1, 3 maps, 5 maps to minus 2, and so on. We can visualize by listing the first few mappings: f1 equal to 0, f2 equal to 1, f3 equal to minus 1, f4 equal to 2, and so on. Clearly, the function covers every integer z in the codomain set exactly once, satisfying the conditions for injection as well as surjection, and proving that it is a bijection or bijective mapping. So, this is the result for bijective mapping. Next question, 4b2. Let rho be an equivalence relation on a set S and A comma B belongs to S, then so that class A equal to class B if and only if A rho B holds. Now the condition is necessary. That is, A rho B holds. A rho B is necessary condition for the condition class A equal to class B to be true. That is, class A equal to class B implies A rho B. Now we first assume class A equal to class B holds. Let X be any elements of class A. So X belongs to class A. This implies and implied by X belongs to class B, because class A equal to class B. Then X row A and X row B hold. Now x row, so x row A hold because x belongs to class A, so x row A hold, and x belongs to class B, so x row B also hold. Then x row A and x row B implies A row X because row is symmetric, row is equivalence relation, so A row X holds, and x row B. So A row X and x row B implies A row B because row is transitive relation. So thus class A equal to class B implies A row B. Now, we want to prove the condition is sufficient. That is, A row B implies class A equal to class B. We assume that A row B holds. We need to show that the equivalence classes of A and B are equal. That is, class A is a subset of class B and class B is a subset of class A. First, we prove class A is a subset of class B. Let X be an arbitrary element in class A. By the definition of an equivalence class, this means that X row A holds. X be an arbitrary element of class A. By definition of equivalence class, obviously X row A holds. So X row A and A row B, because A row B holds, first we assume A row B holds. So this implies X row B because row is transitive. So X row A and A row B implies X row B. So X row B holds, so this implies X belongs to class B. So X is an arbitrary element belongs to class A and implies that X belongs to class B. So for this arbitrary elements X, we have shown that every element class A is also class B. That is, class A is a subset of class B. Similarly, we can prove class B is a subset of class A. Hence, follows that class A equal to class B. This proves the theorem. Note that A row B is a necessary and sufficient condition for class A equal to class B to be true. What is the necessary and sufficient condition? If P be a mathematical statement implies Q be a mathematical statement. Um, P is a mathematical statement and Q be a mathematical statement. We say that P is a sufficient condition. P is sufficient condition. Sufficient condition for for holding Q. The truth of P is enough to guarantee the truth of Q. For example, if you are a dog, then you are a mammal. This being a dog is sufficient for being a mammal. So this is the, if you are a dog, obviously you are a mammal. So this is the dog is sufficient condition for being mammal. Next, P implies Q. We also say that Q is the necessary condition. Q is the necessary condition. Q is the necessary condition for holding the condition P. Q must be true in order for P to be true. If Q is false, then P must be false. That is, equivalently, negation of Q implies negation of P. So P implies Q, equivalent statement is negation of Q implies negation of P. If Q is false, then P must be false. Example, if you are a dog, then you are a mammal. Being a mammal is necessary for being a dog. So mammal is necessary for being a dog, but not sufficient. This here. If you are not a mammal, you cannot be a dog. Next question. For C, prove that for given integers a and b with b greater than 0, there exist unique integers q and r such that A equal to BQ plus R, where 0 less than equal to R less than B. To prove existence, consider the set of non-negative integers S. This is equal to the set A minus Bx such that x belongs to set of all integers Z and A minus Bx greater than equal to 0. We must show this set is non-empty. Is not non-empty. If A greater than equal to 0, we can choose here x equal to 0. So A minus B into 0 is equal to A. This is greater than equal to 0. So these the elements. So A belongs to capital S, because this type of elements of S is A minus Bx, and when A minus Bx is greater than equal to 0 and x belongs to Z, so A belongs to S. If A less than 0, we can choose x equal to A, and since B greater than equal to 1, this condition may be wrong, because this B greater than equal to 1 replaced by this condition is this B greater than equal to 1. We have 1 minus B less than equal to 0. Since A less than 0, so product A into 1 minus B, A into 1 minus B is greater than 0. Then A minus B into A is equal to A minus AB, that is a common 1 minus B. This A 1 minus B obviously greater than equal to 0. So A minus AB belongs to S. So S is non-empty set. Hence, by Euler ordering principle, since S is non-empty set of non-negative integers greater than equal to 0, this A being integers and x also set of integers, AB integers, x is also integers, and this is greater than equal to 0 condition for belonging to S. So by Euler ordering principle, we get a least element say R of the set S, and by the definition of S, this R can be written as A minus BQ with R greater than equal to 0, because R belongs to S and AB are some integers and Q is also integer. Really arranging this equation, we get A equal to BQ plus R, and this is the condition such that A equal to BQ plus R. We get this. So this is the same. This R equal to A minus BQ is the same A equal to BQ plus R. Now we must show R less than B. Let's use a proof by contradiction. Assume R greater than equal to B. Now R minus B equal to value of R is A minus BQ minus B, A minus this B common minus B common bracket Q plus 1. This is greater than equal to 0. This means that A minus B Q plus 1 is also an element of the set S. This R greater than equal to B. So R minus B greater than equal to 0, and hence A minus B bracket Q plus 1 is also greater than equal to 0. This element greater than 0. So this element A minus B Q plus 1 belongs to S. Now R minus B less than R, because B is R is greater than B, greater than equal to B. So R minus B less than R. So R minus B is this less than R. So this element A minus B bracket Q plus 1 belongs to S. R is also belongs to S, and R is the least element of the set S. So this is the least element. So this element A minus B bracket Q plus 1, the R is the smallest element of S, and this contradicts this condition. Therefore, our assumption. So assumption R greater than equal to B must be false. So we must have 0 less than equal to R less than B. This proves the existence of the integer Q and R with the required properties. Now we want to prove the uniqueness of this Q and R. Assume that there are two pairs exist, Q1 R1 and Q2 R2, that satisfying the conditions A equal to BQ1 plus R1 with 0 less than equal to R1 less than B, A equal to BQ2 plus R2 with 0 less than equal to R2 less than B. equating the two expressions for A, we get this A equal to this, A equal to this. So we can write this equal to this, BQ1 plus R1 and equal to BQ2 plus R2. So this implies B bracket Q1 minus Q2 equal to R2 minus R1. This equation shows that B divides the difference R2 minus R1. From the condition 0 less than equal to R1 less than B, 0 less than equal to R2 less than B, we can deduce the range of the difference R2 minus R1. Now, from this R1 greater than equal to 0, from this, that is minus R1 less than equal to 0, and R2 less than B from this condition. So combining this, the R2 minus R1, R2 minus R1, adding this less than B. Similarly, R2 greater than equal to 0, R1 less than B, minus R1 greater than equal to minus B, and this R2 minus R1 greater than minus B. So from this relation, from these relations, we get R2 minus R1 less than B, and from this relation, combining R2 minus R1 greater than minus B. Combining these, minus B less than R2 minus R1 less than B. Now we know that R2 minus R1 is a multiple of B, and its value is strictly between minus B to B by this inequality. The only multiple of B that satisfies this condition is 0. So this R2 minus R1 must be equal to 0, which means that R1 equal to R2, and substituting R1 equal to R2 in the back into the relation, this relation B bracket Q1 minus Q2 equal to R2 minus R1. So this is equal to 0, B not equal to 0. So Q1 equal to Q2, and this proves the uniqueness of Q and R. Next question 4D1. Let f, g maps set of real numbers to real numbers be two functions given by fx is equal to mod x plus x for all x belongs to R, and gx equals to mod x minus x for all x belongs to R. Find f not g. Now we know f not g, this means f not gx is equal to f of gx for all x belongs to set of real numbers R. Now case 1, if x greater than equal to 0, so mod x equal to x, so gx equals to x minus x, because mod x equal to x, so this equal to 0. So f of gx equal to this dx equal to 0, so f of 0, so 0 mod 0 plus 0, that's equal to 0. Case 2, if x less than 0, so mod x equal to minus x, and so gx equals to mod x minus x, so this minus x that's equal to minus 2x. So f of gx equal to f of minus 2x, that is equal to mod of minus 2x plus x, this f of this. Now since x less than 0, so we know that, so minus 2x is greater than 0 because x is less than 0. So mod of minus 2x equal to minus 2x. So f of gx in this case is equal to minus 4x. So combining all these results, we get f not gx equal to 0 if x greater than equal to 0, and this is equal to 4x minus 4x if x less than 0, and this is the find f not g. So this is the f not g. Next question 4D2. If Pn is the prime nth prime, then prove that 1 by P1 plus 1 by P2 plus dot 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 plus 1 by Pn is not an integer. Let the given sum be Sn equal to 1 by P1 plus dot dot plus 1 by Pn. We want to prove Sn is not an integer. We will use proof by contradiction. Assume Sn is an integer for some positive integer n. So Sn equal to k for some positive integer, obviously positive integer belongs to z. It is actually a z plus. Actually, this is the z plus for some positive integers. This is the z plus. Let Qn is the product of this primes P1 into P2 dot Pn, multiplying both sides by this equation Sn equal to k by Qn. So Qn dot Sn equal to Qn dot k. So Qn into bracket value of Sn is the 1 by P1 plus dot 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 1 by Pn equal to Qn into k. Now a Qn equal to the product P1 P2 Pn. So this product P1 P2 Pn divided by P1. So cancel P1 P1. So we get P2 P3 dot dot Pn, first term from this. Next plus second term Qn by P2. Cancel P2. So P1 P3 dot 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 Pn plus so on. And the last term Qn by Pn. Cancel Pn. So we get P1 P2 dot 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 Pn minus 1. This is equal to Qn dot k. Consider the divisibility of each term in the sum by Pn prime integer Pn. The term in the right hand side Qn dot k is clearly divisible by Pn because Qn contains the term Pn, multiple of Pn. In the sum in the left hand side, last term P1, P2, Pn minus 1 does not contain that prime factor Pn. So the term P1 dot P2 dot Pn minus 1 is not divisible by Pn because Pn is a prime number and is not equal to any of the prime P1, P2 dot 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 Pn minus 1. All the other terms in the sum on the left hand side, these first term, second term, and all the terms left hand side contains the prime factor Pn and hence divisible by Pn. But as a whole, the left hand side is not divisible by Pn. So left hand side is not divisible by Pn, right hand side is divisible by Pn. And the initial assumption, this is the contradiction. The initial assumption Sn is an integer must be false. Next, question 4e. If D be the GCD of two non-zero integers a and b, then prove that there exist two integers u comma b such that d equal to au plus bv. Are u b unique? Justify your answer. The theorem stating that the greatest common divisor d of the two non-zero integers a and b can be expressed as a linear combination d equal to au plus bv for some integers u and b known as Bezoart's identity. Now we want to prove the existence of uv. Consider the set S of all positive linear combination of a and b. This is equal to the set ma plus nb such that m comma n belongs to z and ma plus nb greater than 0. Since a and b are non-zero integers, we can choose specific values for m and n to ensure the expression is positive. For example, if a greater than 0, choosing m equal to n equal to 0 and gives this is equal to a, this is greater than 0. If a less than 0, choosing m equal to minus 1, n equal to 0, we get this minus a, and this is greater than 0 because a is negative. Similarly for b, thus a is a non-empty set of positive integers. Hence, by the Weyl ordering principle, the set S must have a smallest element, say D. This D belongs to S. By the definition, the exact specific integers u and b, we get d equal to au plus bv for some specific integers u and b. Integers may be positive or negative. We need to show that this smallest element d is indeed actually the greatest common divisor of a and b. We have to prove two things. To prove d is a common divisor of a and b, and next we prove this d is the greatest common divisor. First we prove d is the common divisor of a and b. Using division algorithm to divide a by d, there exist unique integers q and r such that a equal to qd plus r, where 0 less than equal to r less than d. We know by the division algorithm, if a is divided by d, we get this result. Substitute the expression for d, a equal to q, value of d is this, au plus bv, put here. So this implies a equal to r equal to this. So r equal to a qu minus b qv. So r equal to a 1 minus qu plus b bracket q into v. This shows that r is also a linear combination of a and b. R is a linear combination of a and b. If R greater than 0, then R belongs to S. But we know that R is less than D. From this condition, R is less than D. And D is the smallest element of S. So this is contradiction. R greater than not greater than 0. If so, therefore we must have R equal to 0. This means that A equal to QD. From this R equal to 0, that is R equal to 0. So A equal to QD, because R equal to 0 is the only possible. So similarly argument, we can show D divides B, and thus D is a common divisor of A and B. Next we prove D is the greatest common divisor. Let C be any common divisor of A and B, then C divides A and C divides B. Since D equal to AU plus BB, we can use the properties of divisibility. If C divides A, C divides B, then C must divide any linear combination of A and B. Therefore, C divides bracket AU plus BB, which means that C divides D. C divides D. So C divides D, that is D is divisible by C. That is modulus of C less than equal to modulus of D. This D is positive, so this is equal to actually D. This shows that any common divisor C is less than or equal to D. So D is the greatest common divisor of A and B. Next, we prove the non-uniqueness of U and V by establishing an example. No, the integers U and V are generally not unique. There are infinitely many pairs of integers that satisfy the equation D equal to AU plus BV. If we have one solution UV such that D equal to AU plus BV, we can generate other solutions also. Consider any integer K belongs to Z. A new pair of integers U dash B dash, by this formula, U dash equal to U plus K B by D, and V dash equal to V minus K A by D. Note that this B by D and A by D are also integers because D divides both A and B. Now, for example, A equal to 4, B equal to 6, and GCD of D equal to 2. GCD D 4 and 6 is 2. So 2 equal to 4U plus 6V, and solution for this UV is 2 minus 1, because this 2 equal to 4 into 2 plus 6 into minus 1. Next, using the above formula, K equal to 1. So put here K equal to 1, B equal to 6, B equal to 2, and U equal to 2. So we get U dash equal to another value of U. This U dash equal to 5, and V dash equal to minus 3. Now we check this 4 into 5 plus 6 into minus 3 equal to 2. Thus, UV equal to 5 minus 3 is another valid solution for this 2 equal to 4U plus 6V. If we put K equal to 2, K equal to minus 1, and so on, we get infinitely many solutions for this equation. So UV are not unique in this case. Next, last question 4F. Solved by Chinese remainder theorem, x modulo 1 is x congruence to 1 modulo 17, x congruence to 1 modulo 7, x congruence to 4 modulo 5. The moduli M1 is 17, M2 to 7, M3 5 are pairwise co-prime. So 17 7 GCD1, 7 5 GCD1, 17 5 GCD1. So pairwise co-prime. So Chinese remainder theorem guarantees a unique solution modulo capital M is equal to M1 into M2 into M3. Now we want to calculate this general modulo, this M capital M, and this MI equal to 1 2 3. The total modulus M is equal to 17 into 7 into 5, that is equal to 500. 95. Now we calculate capital Mi. This is equal to capital M by small mi. Small mi is this 17. So capital M1 is this, capital M2 equal to 85, capital M3 equal to this. To find the modular inverse yi, this capital Mi yi congruence to 1 modulo mi. Now from the first, M1 equal to 35, M1 congruent to 35 modulo 17. For M1 35, by modulo 17, that means 35 congruent to 1 modulo 17. 35 because if we divide 35 by 17, then residue is 1. 2 into 17, 34 plus 1 is 35. So this residue, when we divide 35 by 17, residue is 1. So 35 congruent to 1 modulo 17. So capital Mi yi congruent to 1 modulo Mi. So 1 here, this 1, y is 1, y1 congruent to 1 modulo 17, that is y1 equal to 1. For M2 85 modulo 5 modulo 7. So 85, when we divide 85 by 7, we residue gets 1. So this 1 residue 1. So 1 into y2 congruent to 1 modulo 7. Actually, for this M2, we replace this 1 for this one, and y2, this y2, and this congruent to 1 modulo 7. Next, for this M3 119 modulo 5, when we divide 119 by 5, the residue is 4. So capital Mi, in this case 4, capital Mi is 4, put here yi, this y3, this congruent to 1 modulo 5. So 4 into y3 congruent to 1 modulo 5. So actually, if we put y3 equal to 4, then 4 into 4, 16, 16 minus 1, 15, divided by 5. So y3 equal to 4. To calculate the solution x, the formula x congruent to a1 capital M1 y1 plus a2 capital M2 y2 plus a3 capital M3 y3 modulo m capital M. Here a1, a2, a3 are 1, 1, 1, 4. So substituting, we get this equal to 2024 modulo 595. To find the smallest positive solution and reduce this to 2024 is divided by 595. Quotient is 3, remainder is 239. So this reduces to x congruent to 239 modulo 595. And this unique solution modulo 595 is x equal to 239. Actually, 239 is the residue when x is divisible by 595. Check the answer. If we put 239 congruent to 1 in the given system, 239 congruent to 1 modulo 17, because this 239 divided by 17, residue is 1. 239 congruent to 1 modulo 7. So when 239 is divided by 7, residue is 1. So from this equation, given equation is 1. And last 239 is divided by 5, residue is 4. So here the given equation x congruent to 4 modulo 5. So all are solutions are correct. Thank you for watching this video. This completes the group C.